we stated Stampakia's theorem. So, omega in Rn bounded open set 1 less than equal to p less than infinity, and f from R to R Lipschitz continuous function, and f dash continuous except at a finite number of points t1 to tk. Then u in w1p of omega implies f composed with u belongs to w1p of omega, and d by dxi of f composed with u at any x is equal to vi, which is by definition equal to integral f dash composed with u du by dxi if ux does not belong to the forbidden class t1 to tk, and 0 if ux belongs to t1 to tk. I did not prove this, but the complete proof is available in the book Topics in Functional Analysis and Applications, which we are following for this course. Okay, so proposition. So now we proved this theorem in the particular case when f equals mod t, and then we deduce some consequences of that also. Okay, so let u belong to w1p of omega 1 less than equal to p less than infinity, k contained in omega compact, and if u vanishes on omega minus k, then u is in w1p0 of omega. So, if you have a function which vanishes outside a compact set, then that function can be approximated in the w1p norm by means of d omega functions. So, that is what we have to show. So, you have to show there is a sequence of functions in d omega which converge to it. So, choose omega double prime and omega prime relatively compact sets such that k is contained in omega double prime, which is relatively compact in omega prime, which is relatively compact in omega, and let psi belong to d of omega such that psi is identically 1 on omega double prime, in particular in a neighborhood of k, okay, and support of psi contained in omega dash. Then psi u equal to u, because psi u vanishes outside the compact set k, and psi is 1 on the set in a neighborhood of k, and therefore we have seen very often many times that psi u is the same as u. So, let un be as in Friedrich's theorem in d of Rn such that un goes to u in Lp of omega, and dun by dxi goes to du by dxi in omega tilde relatively compact in omega. So, not in for all. So, in Lp of omega tilde for every omega tilde relatively compact in omega. Okay. So, then psi un belongs to d of omega, because psi is C infinity function with compact support, un is also C infinity with compact support in Rn. So, this whole thing is this thing, and support of psi un is contained in omega prime because psi is contained there. Okay, and you have obviously that psi un converges to psi u in LP of omega prime and also LP of omega. So, in fact, in LP of omega. And you also have psi un goes to d by dxi of psi un will converge to d by dxi of psi u in LP of omega prime, because un dun by dxi converges, you are just multiplying by C infinity function with compact support. This will also happen, and this implies, because everything, all supports are contained in omega prime, outside omega prime everything is 0, so implies also in LP of omega, since all functions are 0 outside omega prime. Okay. So then, so this implies that psi of un goes to psi of u, which is equal to u in W1p omega, and this belongs to d of omega. So this implies that psi u belongs to W1p 0 of omega. Okay, so that completes the proof of this result. Okay. So proposition, so omega in Rn bounded open set, 1 less than equal to p less than infinity, f R to R Lipschitz continuous and f dash continuous except T1, T2, Tk at some, except at some finite number of points you have that this is 0 and f of 0 is 0. So if u belongs to W1p 0 of omega, then this implies that f of u belongs to, well, it belongs to W1p of omega by Stampakia's theorem, and we now claim, because f of 0 equals 0 in addition, that it also belongs to W1p 0 of omega. So proof. So un in d of omega, un converges to u in W1p omega. Because u is in W1p 0, so you can always find this. Okay. So now f is Lipschitz continuous, so mod f of unx minus f of u of x is less than or equal to m times mod unx minus u of x, and un goes to u in LP, so you take power p, integrate, you will get that f of un converges to f of u in LP of omega. Also, by passing, if necessary, to a subsequence, we can assume that un goes to u and dun by dxi goes to du by dxi, 1 less than equal to I less than equal to n, pointwise. Because if you have a sequence converging in LP, then there is a subsequence which converges pointwise almost everywhere, and almost everywhere. Okay, and since you have a finite number of such sequences, you can take a common subsequence for which all of these convergences happen. Okay, so then f is continuous, and by formula for derivative of f composed with u, we have that d by dxi of f of un goes to d by dxi of f of u, pointwise almost everywhere, 1 less than or equal to I less than or equal to n, because what is the derivative of f in Stumpakia's theorem? It is just f dash u. So f dash un will go to f dash u, dun by dxi goes to du by dxi, and therefore the derivative will go to whatever we are claiming. Okay, so you have this, and mod d by dxi of f of un minus d by dxi of f of u, each of them is less than or equal to m times, so this is less than or equal to 2m, so this is power p into mod dun by dxi power p plus mod du by dxi power p. Okay, so this just takes the derivative. I am not very sure that I don't think the 2 is necessary, but we will leave it if makes no harm. Okay, so then we have the generalized dominated convergence theorem. What is the generalized dominated convergence theorem? It says that if fn goes to f pointwise, gn goes to g pointwise, and then integral gn goes to integral g, which is finite, then this and fn, sorry, mod fn less than or equal to g, then integral fn goes to integral f. Okay, this is the generalized dominated convergence theorem, where you do have, instead of having dominated by a fixed function fn less than gn, you have by a sequence, but that integral of the sequence converges, so that now all that applies here. So by generalized dominated convergence theorem, we have that d by dxi of f of un goes to d by dxi of f of u in Lp of omega, 1 less than to I less than to n. And therefore this implies that f of un goes to f composed with u in W1p of omega. Okay. Now support of un is compact, f of 0 equal to 0. So this implies that f composed with un equal to 0 outside the compact set. Compact set being the support of un itself, and therefore by the previous proposition we have the f composed with un is in W1p 0 of omega, and that converges to f of u in W1p, and W1p 0 is a closed subspace, and therefore this implies that f of u is also in W1p 0 of omega. So that completes the proof of this fact. So nice corollary of this theorem, corollary. So omega bounded open set, and you have u in W1p 0 of omega, then you have that mod u plus u minus belong to W1p 0 of omega. Okay, so you proof. So you take f of t equals mod t, it satisfies all the conditions of the previous theorem. So this implies that mod u belongs to W1p 0 of omega, and u plus is nothing but mod u plus u by 2, which is equal to max of 0 and u, and then u minus equals mod u minus u by 2, which is minus min of 0 and u, and consequently this implies that u plus u minus are also in W1p 0 of omega. This is a very important observation, though it is very simple to prove, that in fact when you are studying second order partial differential equations, there are something very important results called maximum principles, and the maximum principles come from the observation we have made in this corollary. So therefore it is a very useful corollary which we have. So now one more proposition 1 less than or equal to p less than infinity, omega contained in Rn open set, and you have u in w1p omega intersect c of omega bar. Let us assume that u is a continuous function on the closure. So, if u vanishes on the boundary, then u belongs to w1p0 of omega. So, proof. So, we will do in two steps. So, the first step you assume support of u. Now, that is well defined because u is a continuous function. I can define what is the support. Assume that support of u is bounded in omega. Okay. So, now choose G belong to C1 of R such that mod GT is less than or equal to mod T and GT equal to 0 if mod T is less than or equal to 1 and T if mod T greater or equal to 2. Okay, so you have a function. So you have 0 here, then you have 1 and then you have 2. So in this region you have the function is 0 and from here it is just taking off from T and therefore you have this thing, and so this will automatically imply that mod G prime is bounded. You can always find, so you need to smoothen out between the two some smooth function, one can always put it in. Such functions always exist. Okay, so now you define un equals 1 by n of g of nu. So this implies that un belongs to w1p of omega. So you are using the chain rule, you have multiplied by using nu is also in w1p and g is a c1r function with bounded derivative, and therefore we are in a bounded and g of 0 is 0 and therefore you have that g of un is in this. Now we also claim un goes to u in w1p omega. So let us try to establish this claim. So you have that un equal to u if mod u is greater than or equal to 2 by n. Why? Because then n times mod u, so g of nu is greater than or equal to 2, so g of nu is just nu and you have divided, put a 1 by n in the front, so un is equal to u on this set. And as n tends to infinity, this covers the whole thing, so this implies that un goes to u pointwise. Okay, and also mod un minus u. So mod un is less than or equal to mod gt is less than or equal to mod t. So the 1 by n gnu is the mod is less than or equal to mod u. So mod un is less than or equal to mod u. So this is less power p is less than or equal to 2 power p mod u power p. And this is integrable. So by the dominated convergence theorem, this implies that un goes to u in LP of omega. Okay. Now what about dun by dxi? That is equal to g dash nu, and then the n gets cancelled because when you differentiate with respect to nu, so n du by dxi you will get, and the 1 by n would cancel the n and therefore you just have this. And therefore if n mod u of x is greater than 2, again we have g dash nu is equal to 1. Okay. So dun by dxi also converges to du by dxi pointwise, and again g dash nu, so mod dun by dxi minus du by dxi power p is less than or equal to 2 power p mod du by dxi power p, and this is integrable, and therefore this implies that dun by dxi goes to du by dxi 1 less than or equal to I less than or equal to n in LP omega. Consequently, we have the claim that un goes to u in W1p of omega. Okay. So now what is the support of un? Support of un, u is a continuous function, un is also therefore a continuous function, it is a image by this thing, and therefore this support is again well defined, and this is contained in the set of all x contained in omega such that mod ux is greater than 1 by n, because if nu is less than 1 then g is 0. Okay, so therefore it has to be support like this, but u of x is 0 on d omega, and support is only when u of x is strictly bigger than 1 by n, and therefore this implies that support of un is bounded, closed. It is closed, we know. It is bounded because support of u is bounded, that is where we are using this hypothesis, and strictly contained in omega because of the distance which it has, and consequently you have that un vanishes outside a compact set contained in omega, and therefore by the earlier proposition you have that un belongs to W1p0 of omega, and again you have un goes to u in W1p omega, un is in W1p0, and therefore this shows that u belongs to W1p0 of omega. Okay. Now step 2. So support of u unbounded, of course this makes sense only in unbounded domains. So then you have zeta n is equal to z of x equal to zeta of x by n. This is an old friend where zeta belongs to d of Rn, 0 less than equal to zeta less than equal to 1, support of zeta is in the ball center origin radius 2, and zeta identically 1 on the closed ball center origin radius 1. Then we know that zeta n u goes to u in W1p omega. This is the very first theorem where we proved that W1p Rn is the same as W1p0 Rn. We first convolved, then multiplied by zeta. The convolution gave you a sequence which was C infinity and which converged in W1p. Multiplying by this cutoff function gave you a C infinity function with compact support which goes to. Now support of zeta n u is bounded, and in fact it is contained in omega closure intersection B0 to n, okay, because support of zeta itself is there. So zeta n has support in B0 to n, so this is bounded, and by step 1, so by step 1 you have it's a bounded set, and therefore if the support is bounded, we know that zeta nu belongs to W1p 0 of omega, okay, because it also vanishes on the boundary, okay, and zeta nu equal to 0 on d omega. Therefore by step 1 this you have here, and zeta nu belongs to W1p of omega intersection C omega bar. Everything is there, okay, and therefore you have, since zeta nu converges to u in W1p and zeta nu is in W1p 0, this implies that u belongs to W1p 0 of omega, and that completes the proof. Okay, so now remark. So we have been proving theorems like this. If u is in W1p omega and u equal to 0 outside a compact set, or if u belongs to W1p omega intersection C of omega bar and u equal to 0 on the boundary. All these imply that u belong to W1P 0 of omega. Okay, so what's the moral which we get from this? Namely, if it is 0 on the boundary in some sense, because it vanishes outside a compact set, so near the boundary it is 0, here it is 0 on the boundary being a continuous function, then the function is in W1P 0 of omega. Later on we will show that W1P 0 of omega is precisely the function, set of all functions in W1P which vanish on the boundary in the sense of trace. Okay, so we will trace is what generalizes the notion of value on the boundary, because as I remarked long ago that since the boundary is of measure 0, it does not make sense for an LP function for you to talk about the value on the boundary, but because we know that the function is W1P omega, we use that supplementary information to show that you do have something like the boundary value which can be defined in a nice way, and precisely the boundary value vanishing is W1P 0 omega, and that will coincide with the usual boundary value when you have continuous functions and so on, and therefore that is our aim. So we are making little progress towards that question, and we have proved some particular results.